For this given group, we have actually 6 elements. And let's try to determine whether one or a couple of these elements would generate the given group, and then later on declare that the group is cyclic under addition modulo 6. Yes, if there exists generator, automatically we can say that the group is cyclic. So let's start by using first the first element is 0. This tells us that we are going to operate 0 n number of times, as n number is equal to the set of integers, meaning we're going to operate 0 to itself and then later on repeat and repeat until, if possible, we can generate the entire set or group G. So let's start with 0. Operated with 0, the result is 0 here. So it's actually the set containing 0. If we're going to continue that, you're just gonna repeat 0 and 0 and so on and so forth. But since this is a set, we don't need duplicates, we'll end up here. So obviously, just by trying the element 0 alone, we will have a set containing 0. Since it is not equal to the original Z sub 6 or the group G with element 0 to 5, then 0 is not a generator of the group. But it's not automatically correct to say that it's not cyclic, because if for it to be cyclic, we need to identify at least one, or there is some element that would actually generate the entire group. So let's proceed to our second. We have here 1. So again, we operate 1 to itself. Other references would like to start with 1. It's okay, because automatically it's true. But I would like to start, just for the purpose of discussion, just to be just to be parallel to what I have been doing in the previous videos and on the definition itself. Let me try operating 1 to itself first, and don't worry about that. If it's really cyclic, all the elements will just return in itself. Okay, so let's start with 1 star 1. The result here is 2. So instead of 1, I will start with 2. Again, it's okay, because if we're talking about a set, we can rearrange all elements. Then that number 2 will be operated to 1. So 2 star 1 is actually 3. So 3. Then the 3 will be operated to 1, will result to 4. Using the operation addition modulo 6. And that's why I also place here the Cayley table to be guided. Next, you will have here 4 star 1, which is actually 5. Okay. And then you will have the next one, 5 star 1, according to this operation, is 0. Okay, 0. And then finally, if we're going to operate 0 to 1, you will get 1 itself. If we're going to continue that, 1 to itself, you will still return to 2. And as mentioned, even if you start with that or placing that at the end, it doesn't actually defeat the equality of sets. So that's already okay. And since we have 6 elements, which is the same as our set G or Z sub 4, we can now say that 1 is a generator of your set G or Z sub 4. With this, we can now claim that our Z sub 4 or equal to G is cyclic under addition modulo 6. And this time, we are now done with the identification, because the goal is just to identify or determining whether the group is cyclic or not. So we can stop here. But just for the purpose of discussion, allow me to continue checking the rest of the elements. We still have 4 more, because there might be some questions later on about what are the generators. So identification of 1 is not just enough. But of course, just by identification of 1 will automatically tell us cyclic group. But for the question of how many generators or what are generators, we can continue doing that. Let's continue with for 2. So 2, let's have it here. 2 star 2 is actually 4. Okay? Then you use that. 4 star 2 is actually 0. Then finally, 0. I'm talking about finally because I also would like to add additional concept later on. If you have 0 star 2, so 2, you will get 2. And then if we're going to continue, we just return to 4. My point of saying finally is this. Once you actually reach your identity, because our identity here is actually 0, that's already the signal that you're almost ending your process. Just like here, earlier, when we had 0, this one here, we only have one more attempt and we close that. Similarly here, when you reach 0 and it's obvious that you have not completed some of the elements, automatically we can say that 0 is not a generator because you only have 3 elements here. Okay, so let's continue. How about 3? So we have 3, this one here, 3 star 3 is 0. I'm telling you, once you reach 0, you know what to do next, because it's possible, as it is the identity, when that is actually operated by 3, you just return to 3, and that's it. You only have 2 elements. So 3 is also not a generator of set G. We still have 2 more elements. How about 4? So let's start with 4 star 4, which is actually 2. Okay, then you will have here 2 star 4 is 0. As mentioned, once you reach 0, and since there's only 1 element, obviously 4 is not a generator. But to complete that, you will have here 0 star 4. You will the result is actually 4. Again, 4 is not a generator. How about 5? Okay, is it safe to say that we only have 1 as a generator? Let's try 5. So 5 star 5 is 4. Okay, so you have 4. Then 4 star 5 is 3. Then you have 3 star 5 is 2. 2 star 5 is 1. 1 star 5 is 0. And as mentioned, you only have one more step. 0 star 5 is 5. This is the same as G or Z sub 4. So we can also say that 5 is a generator of your set G or Z sub 4. This means we have here 2 generators, 1 and 5. But again, even just one of them would actually tell us that our group is cyclic. Just for the purpose of the question, how many and what are the generators, we have this step. Thank you very much for watching.